Hey everyone, it's Dr. Calkins, week 6, chapter 6 homework questions, traditionally from students or submitted by discussion forums. So as we look at this chapter, know that most of the answers are going to be on page 50 of your lab book. So on page 50, which is a lab that covers this in detail, we have all of our families, the 4 directions, 4 steric number family, the 3, the 2, remember single bonds, double bonds, triple bonds, all those bond angles that you're going to see. So everything that we're referring to is on page 50. Keep that handy. As we look at number 2, talks about this AB4 molecule. So the best interpretation of AB4 would be methane. And if you look at methane, notice you have this forward and reverse, and then these two that are in the plane of the camera. So we need a wedge and a dash in order to be the answer here. So look for that. Notice if you have 2 wedges, 2 dashes, or something like that, that's going to be something that's probably impossible. They're just trying to give you choices that wouldn't make any sense whatsoever. What we want is a wedge forward and a dash backwards, and that's it. If you're in this AB3 category, this typically means that you've got a double bond. So somewhere in your molecule is a double bond. One of the most common examples we see in lecture for this one is formaldehyde. So formaldehyde is perfectly flat. So if it's perfectly flat, it does shape a triangle. Notice all these are going to shape a triangle. We need everything to be not all forward, not all reverse, but all flat. So we're wanting this one here. So everything needs to be at the same geometric angle. Number 4, it says greatest angle. Well, the greatest angle would be 180 degrees. That's linear. But in order to be linear, you have to have triple bonds, and none of these will. The next biggest angle is 120 degrees, and that's trigonoplanar. So look for that angle. Notice here you have 4 atoms on carbon. Here you have 4 atoms on carbon. And then here you have 4 atoms on carbon. So all of those have the same angle because they all have 4. They're all going to be some variation of, here's methane, which is D. If you have 2 halogens, one that's slightly bigger than the other, basically looks, notice, identically the same. And then even if you have the other one that has 2 chlorines, 2 hydrogens, notice it too, identical. So when you have 4 atoms, you're going to have the same overall shape. So those are kind of a giveaway that the only one left is the answer, and that's formaldehyde that we used earlier. It's going to have only 3 directions because it has a double bond right there to this red oxygen atom, and it's going to have the 120 degree. So all the rest of these are going to have 109.5, so all those are going to be the same. And that tetrahedral angle of 109.5 you can find on page 50. As we look at number 5, it says, who has 180? Well, remember 180 is linear. There's no possible way to be linear if you have 4 atoms, or if you have 3. So you're really down to 2 choices, carbon dioxide if you connect the dots with the 4 and the 6 that we saw on our previous homework. You're going to see 2 double bonds, that's linear. Carbon dioxide makes a good linear molecule like this one. And then water, a lot of students might draw it this way, which is a problem because then it looks linear. But because of those lone pairs, water is actually bent, so be careful. We want linear, this is definitely not linear, that's about a 105 degree angle, this is a 180 degree angle there. So we want CO2. So this is not linear. Oxygen actually has a wedge and a dash on those hydrogens because those lone pairs are so big, that's VSEPR theory. Number 8. Number 8 says a lot of stuff, but what's most important is it says who is most soluble in water. So another way of writing that is who is most polar like water. So when that happens, we have 4 carbon tetrachlorides. So if we look at electronegativity for carbon tetrachloride, we look at carbon first. 2.5, chlorine 3.0. But in carbon tetrachloride we have 4 equal but opposite carbon and chlorine bonds, so that's a 4-way tie. So even though this is 0.5, it's non-polar because it's a 4-way tie. We said watch out for those. Carbon dioxide, saw that one a moment ago. Carbon is, got 2 double bonds, 1 each way. And if you look at electronegativity there, you see carbon at 2.5, oxygen at 3.5. You have a 1.0 to the right and a 1.0 to the left, and nobody wins. So this is a 2-way tie. So even though this is a 1.0 difference, it's also nonpolar because it's the one we said watch out for. So watch out for both of those. Those are planted there to see if you take the bait. You can dissolve ammonia in water just fine because that's how we make a lot of window cleaner. This nitrogen to hydrogen bond. This is a pyramidal structure based on what we would see in lecture. If you look at it, 3.0 and 2.1, that's 0.9. So again, stealing these numbers, 3.0, 2.1. So that 0.9 is going to be reinforced up towards nitrogen each time. Very polar. It's got hydrogen bonding, like water, and we have an ammonia molecule like that. The problem with N2 is you're attached to yourself. When you're attached to yourself, even through a triple bond, 3.0 and 3.0 cancel to 0, and that's the best kind of nonpolar from our last chapter. When drawing a 3D structure, the bold line, as we saw above, and see them in other places, just not as answers, but bold is forward, this dotted dashed line is backwards. So we want out from the page for our bold lines, the dotted lines we want behind the page. Number 11 says not linear. The clue I would look for is if you have 3 atoms, you can't be linear. So boron trifluoride. Boron trifluoride is going to look kind of like this one. So boron's going to have 3 fluorine atoms. It's going to be in this trigonoplanar flat triangle kind of shape. Whereas acetylene, definitely triple bond linear. Hydrogen cyanide, triple bond linear. And then beryllium chloride, you could use this one. Beryllium in the middle, 2 chlorines, still like CO2. And that one's also linear. Number 12 says not tetrahedral. Tetrahedral would be something with 4 bonds. So if we want chloroform, notice it has 4 bonds. That's a perfect tetrahedral, just like methane we saw earlier. Carbon tetrachloride, so it doesn't matter how many attached, it's still got the same number. And if we look at ethane, that's just 2 carbons that are both got 4 bonds. And if we look at, lastly, boron trifluoride, well again, if you have 3, you can't have 4. So boron trifluoride, the winner there again, for the same reason, but for a different question. So again, boron trifluoride is going to be similar to something like this, where you have boron in the middle, 3 fluorines. You don't have that 4th direction, so you're flat. You're not tetrahedral, you're trigonoplanar. 13 says, who has a 105 degree angle that is bent? Tricky one there. Sulfur dioxide is bent. It's just bent 118 because it has that double bond. So that lone pair is coming out of that empty hole there. Water, very similar kind of bent, just at a different angle. So that's the bent 105 that we want. Carbon dioxide, again, is linear. And then ammonia is pyramidal. So we want water for that. Number 14 says who is nonpolar, so this was the less than 0.5 definition in electronegativity. So hydrocarbons, because carbon is 2.5 and hydrogen is 2.1, that difference is 0.4. So methane is CH4, that's a hydrocarbon. Ethene is a larger hydrocarbon, acetylene is still a hydrocarbon, so all of these are going to be nonpolar. That's why oil and water do not mix. 16 says which double bond molecule is polar. So for the same reason, here we have a CS2. Carbon is 2.5, sulfur is 2.5, so that difference is 0. That's nonpolar. This one has a double bond. We have carbon to oxygen, that's 2.5, 3.5, so 1.0, very polar. 2.5, 2.1 on hydrogen to carbon. 0.4 is nonpolar here and there, but we have polarity there, so we have our answer. The problem with students with CO2, they like to take the bait on this one because it is 2.5, 3.5, so it is 1.0, but when you're 1.0 to the left and 1.0 to the right, who wins? The answer is nobody. So this one is the two-way tie. We said watch out for it, and there it sits. SO3 might be another one you want to take the bait on. Here's sulfur and 3 oxygens. Could use that one. Could use this one that's a little more representative of the colors. Same kind of idea though. Sulfur and then 3 oxygens. So this one is 2.5, 3.5, 1.0, 2.5, 3.5, 1.0, 2.5, 3.5, 1.0. That's a three-way tie. We said watch out for those, and in this problem we had 2 of those to watch out for. So by bonds they look polar, but by shape they cancel and they're not. 17 says which one is pure covalent. Remember, covalent means pure sharing, so we're looking for a 0 in electronegativity difference. So when that happens, look for O2, we have oxygen to oxygen. So that's 3.5 to 3.5 in electronegativity on our table. That's 0, that's perfect. Carbon monoxide would be a 2.5, 3.5, that's a 1.0, so that one's polar, not sharing perfectly. Formaldehyde that we saw earlier, we have that 2.5, 3.5, that's polar towards oxygen. And then sulfur to oxygen with 2 chlorines, you're going to be polar this way at 0.5, this way at 0.5, this way at 1.0, because that's 3.0, 3.0, 3.5, 2.5. So that one has polarity everywhere. The only one that doesn't is the one that's sharing with itself. And that's going to be that perfect cancellation. Thing. Number 18 says which one is least soluble in water. So that just means who is least polar. We can definitely see NHs, OHs, and OHs are superpolar. 3.0 on nitrogen, 2.1, that's a 0.9. 3 different ways. Here we have oxygen and hydrogen alone is 3.5, 2.1, that's a 1.4. Superpolar, superpolar. We'll see these in our next chapter as alcohols, very polar. Hydrocarbons are nonpolar. 2.5, 2.1, we saw that up here. They're going to hate water. So they're going to be least soluble in water. What is the shape of H2S? Well, same family, same structure. So H2S ought to look a whole lot like H2O. So both of these have that bent kind of shape that we're looking for H2S. So be careful with this one when you do 6 to 1 to 1. You want to draw it linear. Those lone pairs tell you that this is really what happens. Those lone pairs squish these down together into that bent shape. What about nitrates? Nitrate would be a nitrogen with 3 oxygens. So in this situation we have nitrogen with 3 oxygens. It's in that flat triangular shape. So look at the camera angle, notice there's no left or right, it's just completely in the plane of the camera. But it does shape what looks like a triangle. So trigonal planar. Trigonal because of triangle shape, planar because it's perfectly flat on the side. So trigonal planar is there. '27 says in VSEPR theory, multiple bonds are treated like single groups. That's why single bonds have that family of 4, but double bonds, because single groups are treated even though there's multiple bonds. Double bonds tend to have that family of 3, and then triple bonds tend to have that family of 2. That's again summarized on page 50. So notice even if we have doubles, triples, whatever, we still have 4 total electron groups. It's just now there are some of them in the same direction. So that one there, as you can imagine, is true. Carbon tetrachloride is polar. We said watch out for that one, and this is why. The carbon atom to chlorine is a 0.5, so it's 2.5, 3.0. The subtraction is 0.5. But you have 0.5 up, 0.5 left, 0.5 forward, 0.5 back. Nobody wins. So this is false. It's non-polar because of the four-way tie. So we said watch out for that one. And there it sits. Carbon dioxide has polar bonds. Carbon dioxide we had earlier. Carbon dioxide is got those two double bonds. As we look at carbon dioxide, remember, we saw this one earlier. When you have 2.5 to 3.5, that is a polar bond. So check. Is it non-polar? Well, when you pull at 1.0 to the right and 1.0 to the left through those dipoles, nobody wins. So it ends up being non-polar. So true. Number 32 says bonds. Bonds are negative charge. Well, no duh. They're electrons that are negative. And negative repels negative. So that one's definitely true. So that one's a little more obvious. Just don't think about it too hard. As we look at the lower section, I think we have some on the back. Bond angles. Made some models for these. So here we have ammonia. So it looks like tetrahedral, it's just missing that top atom. So that's because this lone pair that protrudes up is forcing these atoms a little closer together. So that's going to be less than 109 for ammonia. If you look on your page 50, you'd expect nitrogen family atoms to be 107, and that's what we're seeing here. It's going to be close. It's 109 at about 107 for ammonia. Boron trifluoride. Boron trifluoride is going to have something with probably a double bond. So let me find one of those that's going to be close enough. Something like this would probably work. You have a boron atom, and then you have these yellow-looking halogen atoms in this case. Going to be perfectly flat. It's going to shape a triangle. So a triangle would be from those yellow atoms across. So those flat triangles are typically splitting a circle three ways. So 360 divided by 3 is 120. Sulfur dioxide is a tricky one to draw. It's going to break those rules because sulfur is sharing more than once. But notice we have that lone pair here that squishes these underneath to be a little bit closer. It would normally be that flat triangle shape, but because of this squish, it's going to be a little bit less than 120. It's going to be about 118. Sulfur trioxide will be back to normal. So sulfur trioxide is going to have that double bond that puts it in that category of trigonal planar perfectly. So notice that's the major difference between the two. We're lacking that other oxygen. This one has more flex because of that lone pair up here. This one doesn't. So this one's going to be perfectly 120. The ammonium ion. The ammonium ion is going to have basically methane, but with nitrogen in the middle. So the ammonium ion here looks just like methane, but with nitrogen in the middle. Is what happens when it acts as a Bronsted-Lowry base that we'll talk about later in the semester. So here we have four directions. Four directions perfectly is going to be 109.5 tetrahedral. And then lastly, we have carbon disulfide. Carbon disulfide is a lot like carbon dioxide. Sulfur and oxygen in the same family. That's perfectly straight across, and that would be perfectly linear at 180 degrees. This next section is a bunch of rule breakers, so it's a little painful to think about, but here's a fast way to think about it. If you have a methane-like molecule, you're going to have four directions, and you're going to be tetrahedral, but tetrahedral is not a choice. This is the CH3 negative, so here's CH4. If we were to pull a bond off, we would make CH3 negative. And notice now, it is much like ammonia, just with carbon. So both of these have identical shapes now because carbon's missing that bond to hydrogen. And nitrogen's favorite shape is pyramidal, so now it's CH3 negative. HC2 negative is acetylide, so this is from acetylene. This is C2H2. But if we pull off that one, we still have a triple bond. We're still going to be linear. Hydrogen carbonate. Hydrogen carbonate, I don't have one of those made, but here's the basic idea. Ran out of models, atoms, but here's a basic idea. Just pretend those yellows are reds. Here's carbonate, the ion, and then there's hydrogen. If we pull off that hydrogen, or even if we have it on in this case, it doesn't really matter. It's still a flat triangle there that matters. So it's still trigonoplanar. So it's basically, here's carbonate, which is trigonoplanar. Here's hydrogen carbonate, which doesn't change the carbon structure at all. So no change, still trigonoplanar. NH2, well here's NH3. NH2 is going to look a whole lot like water because now they're sharing two bonds, two lone pairs, and we call that bent. As we practice a few of these at the bottom, just remember hydrogen bonding is things like OH or NH or FH that are superpolar. So this is not undergo hydrogen bonding, so not polar is the easier way to think about this. Undergoes hydrogen bonding with water just means it's going to be like water. Water has the OH, so in this case it's going to be polar. So really what we have is A is not polar and B is polar. So as we look at something like CH4, and we saw this a moment ago, you have 2.5, 2.1, that's 0.4, that's not enough. So not polar does not interact with water through hydrogen bonding. We'll talk about hydrogen bonding in more detail in about 3 chapters. But when you get down to this one here, we see carbon is 2.5, oxygen is 3.5, that's a 1.0. That is polar. All we needed to be was 0.5, and this is double that. So there we're going to be more capable of hydrogen bonding, specifically towards this double bond oxygen up here. It's going to be very electronegative. It's going to attract water through an attraction we call intermolecular forces in hydrogen bonding later. So hydrocarbons can definitely be non-polar. Anything with oxygens or nitrogens is probably going to be polar, so I can help you in that section. Our last section, very similar. Remember, with polar and non-polar, we're looking for less than 0.5 in electronegativity. And then polar is more, so 0.5 or larger in electronegativity. And that'll work for all of these except for the 2 that I have highlighted. We said watch out for 3. We said watch out for CO2, SO3, and CCl4. That's a 2-way tie based on shape for CO2. So we saw that one earlier. We have SO3, which is a 3-way tie. So watch out for that one. And then we have our 4-way tie, which is CCl4, which is this one. So those are the ones to watch out for because they cancel based on their shape. Otherwise, you're going to say 1.0, 1.0, 0.5, 0.5, 0.5, or 0.5, 0.5, 0.5, 0.5. And in all those situations, nobody wins. So watch out for those, because even though if you do the subtraction, you're going to think 2.5, 3.5 should make you polar. This one's actually non-polar, because it's that 3-way tie. CCl4 wasn't a choice, it was in the true and false. CO2, you're going to think 2.5, 3.5, that's 1.0, definitely polar, but 2-way tie, so non-polar. So worry about shape, but for all the rest of them, you can probably just find their numbers on the electronegativity table, subtract, and not worry about shape. So that does it for this homework. We'll see you next time.